Hello, and in today's episode of Ty Does Maths, we'll be looking at the question 11, the last question on the 2019 AS Maths paper from OCR. Maths and Mechanics, H230. So here's the question. We've got this little scenario. This is all describing what's happening. So two balls P and Q of masses 3 and 2, so that's those two. The ball's attached to the end of a string. This P is held on a rough horizontal surface, so this is rough, so there's going to be friction. The string passes over a pulley which is fixed at the edge of the surface, so that's all that is. The Q hangs vertically below the pulley at a height of 2 meters above the horizontal floor. That comes into play later on. The system is initially at rest with the string tight, taut. A horizontal force magnitude 40 acts on P, as shown in the diagram. There's the force, somebody's pulling it along. P is released and moves directly away from the pulley, so everything's moving this way and the Q is moving upwards. A constant frictional force of magnitude 8, so there's 8 on the pulley, just pulling backwards. Opposes the motion of P. It is given that P doesn't leave the horizontal surface and Q does not reach a pulley in the subsequent motion. The balls are modelled as particles. The pulley is modelled as being small and smooth, and the string is modelled as being light and extensible. Show that the magnitude of the acceleration of each particle is 2.48. Okay, so here we go. So I'll say number 1, draw the picture. So we've got our own picture going on. We've got 3, we've got a frictional force of 8 going that way, we've got a pulling force of 40 that way, we've got acceleration going this way, we come to the pulley, then down, we've got a tension in the string, tension in the string going upwards as well, which is the same. We've got 2 there, we've got 2g coming down, which is just the weight, we've got the acceleration, same acceleration going up because they're tied up. We then go for resolving the forces, and I'm going to resolve upwards to kick off with, I think. So resolving upwards on this one, I've got the T there, so tension, take away the weight, 2g equals a mass times acceleration, so that's just forces mass times acceleration, and that gives us T equals 2a plus 2g, just shifting this onto the other side. Okay. Next step, we resolve with the direction of motion, so we're going to go this way. We've got 40, take away the 8, take away the tension, equals the mass of 3 times acceleration a. Now we know the tension is this thing, so I can just throw that in there, and this is obviously just 32. So 32 minus 2a plus 2g equals 3a. We can move this minus 2a onto this side to make it 5, and we'll just change that to 19.8. 2 lots of 19.6, isn't it? What we're talking about. So we'll do that takeaway as a calculator. I was doing sums on a calculator so you're not making any stupid mistakes. So 32, yes it was, take away 2 times 9.8, which is the gravity, and I've got 12.4. So 12.4 equals 5a. We'll move that 2a across, remember. Just divide by 5, and a equals 12.4, there it is there, divided by 5, and I've got 2.48 meters per second squared as required, smiley face, QED, whatever you want to write. Okay, the next step is to find the tension in the string. Well, we already know tension is this thing up here, so we've got tension equals 2 lots of the 2.48 plus 2 lots of the gravity, which equals, let's go to the calculator, so we want 2 lots of 2.48 plus 2 lots of the gravity, and that's giving me 24.56 newtons, 24.56 newtons as the tension. Okay. Right, next step, we've got when the balls have been in motion for 0.5 seconds, the string breaks, find the additional time that elapses until Q hits the floor. Now what's happening at 0.5 seconds, the ball's been travelling upwards, the string snaps, it still travels up a little bit more, then it comes down and hits the floor again. So first of all, what I want to know is how fast it's travelling at this particular point. Okay, so what I'm doing is just a SUVAT, so SUVAT. Obviously all the really bright people write SUVAT along the line, they don't write it down like weirdos. SUVAT, what am I looking for? I know that this is 0.5. I know once it's been travelling, so I know the acceleration is 2.48 up until that point. We know the initial speed is 0, and what we're looking for is how fast it is when it's starting to when it snaps. So I'm looking for v there. Okay, so I've got v equals u plus at equals u plus at, so v equals u is 0 and half of 2.48, so well, let's just put that in plus 2.48 times 0.5, which is obviously equal to 1.24 meters per second. Okay, so that's how fast it is traveling when it first snaps. Now what we're going to do now is just run a SUVAT again, S-U-V-A-T. Now this time I'm going to be a bit sneaky because I'm going to say it's traveling upwards at 1.24, so 1.24 there, and this is from the point it's been traveling is, so I need to find out, sorry, what am I trying to look for now? So I want to know how far it's traveled before the string snaps, don't I? So I want to know that distance I've travelled. Let me think, what am I doing here? I want to find this distance here. I know the time is 0.5. I know the, let's just cross that out. I know that this is here is going to be 0. No, what is that? It's 2.48, isn't it? So that was the acceleration, 2.48 from up here somewhere. And we know it started at 0, not that's one thing I don't even know what I'm talking about there. So that's the formula, that's the information I've got. So I'll have the speed it's travelling and I know how high up it's gone. Let's just have a look. So we've got SUVAT again. No, we've got S equals UT plus a half of AT squared. We're looking for S, so we can put that in there. S equals 0 times 0.5 plus a half times 2.48 times by 0.5 squared. So the distance it's travelled up to that snapping point. Get your calculator again, so that's obviously going to be 0. Let's just do this bit. 0.5 times 2.48 times 0.5 squared, and that's going to be 0.31 meters, so 0.31 meters. Okay, so we've got this information here and we've got this information here. Right, so let's have a look what's going on here. So now I've got this particle here and I'm travelling this way. I'm at a height currently at a height of 2.31. Now the 2.31 was the initial height, and then the 0.31 that it's travelled upwards. We're going upwards at the moment, and we've got our speed at this point, so u, which I'm going to call the speed that I'm starting at now, because this is a new setup, is 1.24. So I've got 1.24 there. Now if I use SUVAT, I can be a bit tricky and do a little trick here. So S, U, V, A and T, obviously written crossways, not downwards like a weirdo. The distance I've got to fall is down there. I'm going to put that as minus 2.31 because I'm saying this is my ground 0 and then I've got to fall this one. So I'm travelling at 1.24 and that's positive because it's going upwards. The only thing that's slowing me down is gravity, so minus G. And the thing I'm looking for, it says find the additional time, so I want to know what this time is here, so I want to know what T is there. So the formula for that one is S equals UT plus half AT squared. So S equals UT plus half of AT squared. So let's go for that one. So now I've got S equals minus 2.31 equals 1.24T plus 0.5 times minus 9.8, and then I've got T squared there. So let's just tidy everything up there. So that's going to give me, so I'll just leave that alone a minute, minus 2.31 equals 1.24T minus, because it's at that one, then 4.9, half of 9.8, T squared. Shift everything over here. I'm going to have 4.9 T squared minus 1.24T, take away 2.31 equals 0. This is just a quadratic in T. And at this point I'm just going to use the quadratic formula. So I've got A equals 4.9, B equals minus 1.24, and C equals minus 2.31. Okay, this is how I'm going to go about this thing. So quadratic formula goes, press the buttons on our calculator again now. So we've got the fraction, we've got minus, and in brackets we put our B, minus 1.24 bracket, plus the square root of bracket minus 1.24 bracket squared, take away 4, lots of A, and then lots of C, which is minus 2.31, brackets, all over 2 lots of A's, so 2 lots of A's are 4.9, close my bracket. That's just the quadratic formula. And there you go, I've got 0.8246, so T equals 0.8246 whatever, which equals 0.825 seconds. Now, just as a bit of a query, what happens if I just do the takeaway version of the square root? Let's have a look what's going on there. Oops, delete and take away. and I'm hoping for a negative time because that's the one that I can ignore, because obviously we're not time travelers and we're not going to go backwards in time. So that's that one. Find the speed that hits the floor. Let me just put that back into the calculator, the actual time that we have, so we can use that information if we want to. So delete and then do a plus there instead, and there's that number. It's always nice to have the exact numbers when you're playing about these things. So we've got, let's have a look, S is minus 2.31, U equals 1.24, V we've now got as 0.82, oh no, that's not right, that's not V, does it? We'll look for V. A equals minus G, so minus G, and T equals this number here, 0.825. And now I'm going to just use V equals U plus AT, U plus AT, which equals 1.24 plus minus G, so we've got minus 9.8, and then we've got T, which is 0.825-ish, and then we just use our calculator for that bit. So we've got 1.24, take away 9.8 times that last answer that I had, and I've got a speed of, well, I've got a minus 6.84. Now the only reason it's a minus is because we took our positive direction going upwards, so that's the velocity. So the speed is equal to 6.84 meters per second. Okay, so that's the actual speed. This was the velocity that included the actual direction you were going. Write down the magnitude of the normal reaction force on Q when Q comes to rest at the floor. So when Q is on the floor, so we've got this weight here of 2. There's the floor. We've got 2G is the weight passing downwards. Your normal reaction, called R up here, is just equal to the weight, isn't it? So the normal reaction, R, is just equal to 2G. And we can take our calculators and we can work that out. It's just 19.6 newtons is your normal reaction. That's just when it's sat still on the floor. And then the last part says state one improvement that could be made to the model, and you can just basically waffle here. And I'm just going to go with, we use G as 9.8, let's just say more accurate use of, so more accurate value for G, because I've just used 9.8. Let's just use a more accurate one, and then you'll be good to go. And that was it. That was the last question on the AS paper. Okay, bye now.